Okay, this is section 2.8. We are going to start getting really into the applications of derivatives. The first one that we're going to talk about is this thing which is called related rates. Now, if you think about the title, it actually pretty much spells it out for you. We've got rates, specifically rates of change, and somehow they are all related to each other. The most difficult part of this particular section is that these are word problems, so we kind of have to decipher exactly what it is that we're looking for. And we're going to go through several examples of related rates. And the unfortunate thing about that is, doesn't matter how many examples we go through, there's always going to be something else out there that's not going to look like this. So there's so many possible things you could have for related rates that there's just no way of possibly going through every single type. But we will cover a decent amount of them. So hopefully you start to get the idea of what to look for. Okay, so let's talk about the idea, first of all, of a related rate. So when two or more variables satisfy some relationship over time, and some knowledge of the rate of change of one of the variables with respect to time, is known, and we wish to find the rate of change with respect to time, of the other variable, we can apply related rates. So ultimately what this is saying is you got two or more variables, excuse me, both of which or all of which are changing with respect to time. So everything in there has got some possibility of multiple variables changing over time. Somehow they are related to each other within some kind of an equation. So we're going to have to apply related rates. Ultimately, that's just kind of a fancy way of saying we're going to have to apply the chain rule as well. And the chain rule will be done for everything that's changing over time. So example one, here's the general idea. Two variables, x and y, are functions of a variable t. So that means both x and y are dependent upon the variable t. T is now the independent variable. And they're all related by the equation x cubed minus 2y squared plus 5x equals 16. You might look at that and say, wait a minute, there's no t's in there. That's true, there aren't. But it doesn't mean that they aren't changing over time. So x and y here are changing over time. So we want to differentiate with respect to t using the chain rule. So the concept is really simple. Basically, it's anytime you take a derivative of something where it is changing with respect to another variable, you have to apply the chain rule. So when I take the derivative of x cubed, it's going to be 3x squared, but x itself is changing over time. So now we have to take the derivative of x, which is dx over dt, because it's changing over time. X is changing the dx over the change of time, dt. Every variable will be treated the same way. Minus the derivative of 2y squared is 4y, but y is also changing with respect to time because it tells us that in the problem. So it's dy over dt. That's the chain rule. Plus 5 times dx over dt, because that's the derivative of x. And then on the right side, the derivative of 16, because its constant is 0. And that's it. That's how you end up taking the derivative of something with respect to time. So the resulting equation involves in rates of change dx over dt and dy over dt, where dx over dt, there should be a period here, where dx over dt and dy over dt are called related rates because they are rates of change. They are related to each other within the same equation. Okay, let's go ahead and look at some actual word problem examples. Now we'll try and start off with one that is relatively basic, but I think it'll walk us through how and what we should be looking for. Okay, so it says, a ladder 20 feet long leans against the wall of a vertical building. If the bottom of the ladder slides away from the building horizontally at a rate of 2 feet per second, how fast is the ladder sliding down the building when the top of the ladder is 12 feet above the ground? Got it? Everybody knows all the information? Yeah, me neither. So you got to go back and you got to read these things multiple times sometimes. Okay, you can't just read it one time and be like, oh, I know everything. If you do, awesome. But most of us are not going to be able to do that. So we're going to go back. So we've got a 20-foot ladder leaning up against the wall of a vertical building. Let's start there. I am not an artist, but I will do my best to sketch this. So here is my vertical building. There we go. I got a 20-foot ladder leaning up against the wall. I can do that. That's a 20-foot ladder leaning up against the wall. Matter of fact, we'll label that 20 feet. If the bottom of the ladder slides away from the building horizontally, so here's the bottom of the, here's kind of the ground, I guess. And it's saying that the bottom of the ladder, which is here, is sliding away from the building horizontally. So it's moving in that direction at a rate of 2 feet per second. So it's moving to the right at 2 feet, at 2 feet per second. How fast is the ladder sliding down the building? So we're looking to figure out how fast this thing is coming down the building when the top of the ladder is 12 feet above the ground. So it's telling me that at the instant that I want to know how fast this thing is sliding down the building, this thing right here is 12 feet above the ground. It should be feet right there for the 20. All right, so I've kind of labeled mostly everything. Now we have to figure out, okay, first of all of these things have to be related somehow. I've got to start applying variables to things. Well, it should be relatively obvious that we have formed a right triangle, okay? And the easiest equation to use here for this specific right triangle, because all we're talking about are the lengths of the sides here, is the Pythagorean theorem. The Pythagorean theorem relates all three sides of this right triangle. So let's go ahead and write out the Pythagorean theorem, which is x squared plus y squared equals z squared. Now we'll kind of look at this building and the ground here as being like our x and y axis. So we'll call this kind of our x distance and this kind of our y distance, which means that the z is going to end up being the hypotenuse here. So we'll have the z as the 20 feet. Okay, so now let's go ahead and we're going to take the derivative of this with respect to time, because according to this, everything is changing with respect to time. It's got some kind of a related rate to it. I've got multiple rates. So let's go ahead and take the derivative. So we're going to get the derivative of x squared, which is 2x times dx over dt, plus 2y times dy over dt equals 2z times dz over dt. One nice thing is here is I can simplify this a little bit because I can divide 2 out of both sides because I've got a 2 in everything, so those are going to go away. So what that leaves us with is x times dx over dt plus y times dy over dt equals z times dz over dt. So we have to figure out now what information of this was given to us and what we're trying to find. Well, we have, according to our current formula, I've got 6 unknowns. I've got x, y, and z. I've also got dx dt, dy dt, and dz dt, all of which are currently unknown values. Let's figure out what we've got. Okay, so I know that z is 20. Okay, that is this part right here. This is my z value. I know that y is 12. That's that one right there. I can find x. It didn't give me x, but I can find the length of that piece from basically from here to here because it's part of a right triangle. So if you plug 20 and 12 into your standard Pythagorean theorem, you would find that this length would be 16 feet. Okay, I'm not going to work that one up, but you would find that that length would be 16 feet, and that is your x value. So we can fill those in. Let's go ahead and fill in the knowns. X is going to be 16, y is going to be 12, and z is going to be 20. So now let's figure out what it is that we're looking for. What else we have? Well, I know that the excuse me, the horizontal piece is moving away from the building at 2 feet per second. Well, that's the x direction. So we're going to call this right here our dx over dt. That's how x is changing. The x, or the ladder on the bottom there, is sliding away from the wall. So technically it's affecting how long the length is of the x value. So that's going to be dx over dt. So I'm going to fill that in as 2. According to this, I'm trying to figure out how fast this thing is sliding down the wall, which is that vertical arrow on the y-axis. I am looking for dy over dt. That's kind of my unknown value. That's what I'm trying to find. So over here, I'm just going to write dy over dt because that's what I'm trying to solve for. So the only other thing I have to figure out is dz over dt. Well, you got to think about this one for a second. It says it's a 20-foot ladder. The ladder is sliding down the wall. It does not say that the ladder is getting longer or shorter. It's just sliding down the wall. Therefore, z itself is not changing. The length of the ladder is not changing. Therefore, dz over dt is 0. And we can write that up here if we want to. dz over dt is 0. It's not changing. So now I have everything that I need. Now, normally I wouldn't do it in this order. I'm going to go back and I'm going to write the stuff that you see up there where it says given, find, and when, because we kind of need to be able to figure that out up front. But I really wanted to walk through this as far as the different parts here real quick. So the given information was that dx over dt was 2 feet per second. We want to find dy over dt, that's the unknown. And the when part is we want to do this when the top of the ladder was 12 feet, which means that the y value was 12. Okay, and that's what it told us in the problem. And again, you'd have to go back and reread that a couple of times sometimes to pick all this stuff out. But that's what we're looking for. Okay, so now we can pretty much solve for dy over dt. Right side of the equation is pretty easy. That's just 0. Left side is going to give me 32 plus 12 dy over dt. Subtracting 32 on both sides is going to give us a negative 32 on the right, and then dy over dt, dividing both sides by 12, is going to give us negative 32 over 12, which will reduce, 4 goes into both of them, so negative 8 over 3. And because it is a rate of change, we need units. Well, let's see, it is going to be, what were we given here? It was feet per second. So it's going to be changing at a rate of negative 8/3 feet per second. Okay, now we have to be able to actually state this in a statement. And this is a little bit tedious, but I strongly urge you to get good at doing it this way. So you have to be able to state what's going on. So there are kind of 3 things that you want to state. You want to state what is happening, when is it happening, and how is it happening. What, when, and how. Doesn't really matter the order as long as what you write makes sense. So what is happening is that the ladder is moving down the wall. How is it happening? At 8/3 feet per second. And when is it happening? When the top of the ladder is 12 feet high, or 12 feet above the ground. So what is happening? The ladder's moving down the wall. How is it happening? At 8/3 feet per second. When is it happening? is at when the top of the ladder is at 12 feet high. Now, one thing I wanted to point out, notice here that I did not write that the ladder is moving down the wall at negative 8/3 feet per second. The negative indicates direction. So if I just said that the ladder is moving at negative 8/3 feet per second, that would be okay. But since I already stated down, if I said something is moving down at a negative rate, it actually, as a double negative, it indicates that it's moving up. So you want to be careful about that. If you've indicated direction in your verbal statement, do not indicate direction with your positive or negative signs. So just make sure that you're careful about double negativing yourself or something like that. Okay. So that's it. I mean, that's one problem. A triangle problem is a standard way to start. Something with Pythagorean theorem is relatively common, and you'll get to see those types of problems. But of course, they're not always going to be with triangles. Sometimes they will, sometimes they won't. Like example number 3 here. So it says, the radius r of a sphere is increasing at a rate of 2 inches per minute. Find the rate of change of the volume when the radius is 6 inches. And then it says, explain all this other stuff. We are not going to do that. Not that it's not useful. I'm just not going to cover it right now. So we're just going to focus on the top part. The radius of a sphere is increasing at 2 inches per minute. Find the rate of change of the volume when r is 6 inches. So the first thing you have to ask yourself is, do I know a formula that has both the radius of a sphere and the volume of a sphere in it? Well, hopefully you remember that the volume of a sphere has the radius in it. The volume of a sphere, if you don't remember the equation, is 4/3 pi r cubed. That is the volume of a sphere. If you remembered that, that's awesome. If you didn't remember it, here it is. So we're going to go ahead and start by saying, okay, what was given to us? The radius of a sphere is increasing. So that's telling me right there, the radius is increasing, tells me that it's a rate of change. So the radius increasing is going to be dr over dt, and it tells us that it is 2 inches per minute. 2 inches per minute. Find the rate of change of volume. So it wants me to find the rate of change of the volume, which is going to be a dv over dt. That's what we're looking for when it says r is 6 inches. So it kind of spelled that one out here for us for the most part. So now we can go ahead and figure this thing out. So the first thing that I need to be able to do is I need to be able to take the derivative. Well, if you take the derivative of one side of the equation, you take the derivative of the other side of the equation. That's how it works. So I'm going to take the derivative of v, which is going to be dv over dt, because it's how the volume is changing over time. The right side of the equation, be careful because pi is not a variable. Just remember that. Pi is a constant. So really r is the only thing on the right side, and r is the only thing that's changing. So all we have to do is use the power rule. We'll bring the 3 out to the front. If you multiply 3 by 4/3, you just get 4, because the 3's will cancel out. So you get 4 pi r squared. Don't forget, r is changing over time, so you got to multiply it by dr over dt. So now it says we're looking for dv over dt. Do we have everything that we need? Do we have r and do we have dr over dt? We do. So all we have to do now is plug them in and get a value. So we've got dv over dt is going to be 4 times pi times the radius, which was 6 squared, times dr over dt, which is 2. So now let's figure out what the value is here. Anytime you can do an exact value, by the way, and leave things in terms of pi, it's most likely that's what you're supposed to do. If it says to approximate something, then you're going to use the value of pi, either 3.14 or the actual pi button, which is more likely what you would have to use. Okay, so let's see. What do we have here? You should be able to try and do this mentally. So 6 squared, remember you can multiply in any order, by the way. So 6 squared is 36, times 2 is 72. Then I have to multiply that by 4. So 72 times 4. Well, 72 times 2 more is 144 times another 2, because I'm multiplying by 4, is 288. So we get 288 pi. Now we have to come up with the units. Well, this is how volume is changing. Volume is a three-dimensional thing. So it's going to be changing by something cubed per time. And I think it was inches. Yep, it's inches. So it's going to be inches cubed, because it's volume, three-dimensional, per time, per minute. 288 pi inches cubed per minute. And then we need to go ahead and write our statement. What is happening? The volume of the sphere is changing. Notice I didn't say increasing here. I said is changing by 288 pi inches cubed per minute. So that's the what is happening, that's the how is it happening, and the other thing is the when is it happening, and that was when the radius is 6 inches. So the important thing about that, I mean, the sentence itself wasn't that difficult to write, but the important thing about this one, or about all of these, is the when part. Okay, because the rate of change of the volume is going to be different depending upon the when. If we waited until this sphere had expanded to 10 inches of a radius, the rate of change of the volume is most likely going to be different. So it's at a specific moment in time that we're actually finding this. Therefore, the main thing I want to get across there is you can't plug these things in early. You have to take the derivatives first, because we need to know what's happening at that specific moment of time, how something is changing at that one moment in time. The only time you can plug something in early is if that thing does not change. Well, the radius was changing, so you couldn't plug a 6 in early and then figure out what it is after that. You have to wait. So only time you can plug something in right away is if that piece specifically does not change. All right, that is plenty long enough for our first video. We will come back with a second video, and we may have to do a third because these are not short problems. We'll see.